right, so we can resume this morning session with a long talk on TNOs by Alessandro Morbidelli. So it's a 40-minute long talk, and again, I will give 5 when you have 5 minutes from the end.
Okay,
please.
So, thank you for coming back, and thanks to the organizers for inviting me to give this talk. So I would like to go back to some real astronomy and present this work that I did with Konstantin Batygin at Caltech about the dynamical evolution of distant trans-Neptunian objects induced by Planet 9. So the story of Planet 9 starts with the observation that the most elongated, the most elliptic trans-Neptunian objects have orbits which are not isotropically distributed in space, but are more or less aligned in one direction. That means that the longitudes of the perihelia of these orbits cluster within 90 or 100 degrees. And this is in contrast with the orbits which are less elongated, which are here shown in red. And they are more isotropically dispersed. And actually the less elongated is an orbit, the more isotropically is the distribution. And this is, of course, just the projection of the orbits on a plane. But we can try to give a three-dimensional representation, which is what they do here. So here the plane of the screen is the ecliptic plane. And for each orbit, in the thick line shows the part of the orbit that comes out of the plane towards you. And the thin part of the line is the part of the orbit which is behind the plane towards the garden. And so you can get an idea of the 3D distribution of these orbits. And also, and again, you see that these orbits are not distributed at random. The orbits cut the projection plane, cut the ecliptic very close to perihelion. And when they do so, they always go from below the ecliptic to above the ecliptic, never the opposite. They never go down, they always go up. Which means that the argument of perihelia are clustered around 0. And this was noticed already by Trujillo and Shepard in 2014. So we have a double clustering of the most eccentric trans-Neptunian objects. We have a clustering in the longitude of perihelion and a clustering in the argument of perihelion. And Batygin and Brown, in their paper in 2016, computed that the probability to have this double clustering by chance is very tiny. It's for the order of 0.007%. So they propose that actually this double clustering is due to the presence of a planet, and they show that the planet that can do this confinement is a planet of the order of 10-15 Earth masses on a very elongated orbit, so with an orbital period of about 15,000 to 20,000 years, and which has to be anti-aligned with respect to the orbits of the TNOs. And in their paper, they also show something very interesting. At the beginning, the elongated TNOs should have had orbits in every possible direction. These elongated TNOs are actually planetesimals that were in the giant planet region and that have been scattered on eccentric orbits by the giant planets. So you expect that the scattering occurs in every direction. But as time progresses, if you have an outer elliptic planet, this distribution loses its isotropic character. And as time goes on, you get more and more orbits elongated in the opposite direction of the planet and fewer elongated in the direction of the planet. So this movie is rather long, so, and also with the lights on, you don't see it very much. So we pass on in terms for sake of time. But believe me that at the end of 4 billion years of simulations, all the elongated orbits are on this side and there are none on the side of the planet. Nevertheless, in the original paper of Batygin and Brown, where mechanisms that led to this orbital confinement were not absolutely clear. And since 2016, new objects have also been found. And some of these objects don't cluster with the others. So for instance, two bodies have been found on orbits which are elongated in the opposite direction of the original clump. And one object has been found even with an orbit which is 90 degrees of the clump, which made some observers to shout that Planet 9 certainly does not exist. So the situation is rather confused, and that's why we decided to do a real celestial mechanics study to see what are the effects of an elliptic outer planet on the distribution, on the orbital evolution of elongated TNOs. And regardless of whether or not this planet exists, I think this is an interesting study from the celestial mechanics standpoint, because the restricted free body problem historically has always been studied by considering planets on a small eccentricity orbit, because we're inspired by Jupiter. And here we need to do the restricted free body problem with a perturber on an extreme eccentricity. So let's see, well, the original paper by Batygin and Brown insisted that mid-motion resonances with Planet 9 were very important. And after that, Hervé Burst and Grenoble pointed out that actually mid-motion resonances are not needed at all in order to have a perihelion clustering, because the secular dynamics creates this libration of perihelia around, anti-aligned with the perihelion of Planet 9. So we checked that. So this is a secular diagram showing the evolution of the eccentricity of a particle as a function of its difference, the difference between its perihelion, longitudinal perihelion, and that of Planet 9. And this diagram is computed by taking the Newtonian and averaging it over the mean longitudes. And yes, you see an equilibrium point here with at 180 degrees and libration trajectories. But the point is that these orbits here are not protected from close encounters and from collisions from the planet. Actually, all the orbits in this part of the diagram suffer close encounters with Planet 9. So a very unstable semi-major axis keeps hopping around and so on, and eventually within 4 billion years they would be lost. The curves look smooth because the singularity is integrable. It's something that Giovanni Gronchi worked a lot during his thesis, but nevertheless, close encounters and collisions are possible. The singularity is not integrable only along these two lines, and these are the lines where the two orbits are tangent. So the only portion of the phase space which is protected from close encounters and collision is this little portion here, where actually the perihelion librates around 0. The difference of perihelia librates around 0, so not around 180 degrees as observed. But as you can see, the eccentricity for this stable heaven is pretty low, so we are very far from the Neptune crossing line. So bodies down here, maybe they do exist, but they are very difficult to observe because the perihelion distance is very far away. So unless they are gigantic and very bright, current telescopes will not be able to detect them. By the way, this secular diagram has been computed assuming that Planet 9 has 10 Earth masses, has a semi-major axis of 700 AU, has an eccentricity of 0.6, and it's on the plane of the solar system. And of course, to compute this kind of diagrams, we don't do any kind of series expansion that would never work for this kind of eccentricities. We do all the averaging in a closed form, numerical. So when we do actually a numerical simulation, what do we see? So we did, for instance, a 4 billion year numerical simulation with Planet 9 and the trans-Neptunian objects, for simplicity, on the same plane. The initial conditions for the trans-Neptunian objects were had a perihelion close to Neptune between 30 and 36 AU, and semi-major axis between 150 and 750 AU. We don't put the inner giant planets, but we put an artificial J2 to the sun, so that the force precession given by the inner giant planet is there. And we don't want to have the inner giant planets to avoid the scattering of Neptune, which would make the dynamics more complicated to analyze. And the histogram down here shows the semi-major axis of all the particles that survive for both 4 billion years. So as you can see, the semi-major axes are not randomly distributed. This histogram is actually made of distinct lines, each line corresponding to a mid-motion resonance to Planet 9. So only bodies in mid-motion resonances do survive for the age of the solar system. The outermost resonances, so the resonances closest to Planet 9, like 2-1, 3-2, 4-3, 1-1, and so on, all these stable resonant objects have the perihelia in apsidal libration around the perihelion of Planet 9, and this apsidal libration is around 180 degrees. So they do form this cluster. But the more distant resonances, like the 3-1, 4-1, 5-1, and so on, they can have both orbits in apsidal libration around P, but also orbits in apsidal circulation. So you can see also orbits with any kind of longitudinal perihelion. And actually, if you look carefully, there is a solid bold segment and then a gray segment, and the ratio between the length of these two segments gives the relative fraction of bodies with upsidal circulation versus upsidal libration. So the distant resonances of high order can have both, and the resonances close to planet 9 can only have upsidal libration. Let's look a little bit, before going into the model, what happens for an orbit in upsidal libration. So for instance, an orbit in the 3-2 resonance with planet 9. So here we see, as a function of time, over 4 billion years, the oscillation of the eccentricity of the TNO, which is perfectly correlated with the libration of its perihelion around the perihelion of planet 9. This is the difference of perihelia librating around 180 degrees. It's a 3-2 mean-motion resonance, so there are two critical angles of the mean-motion resonance. K is 3, L is 2. The lambdas are the mean longitudes, and varp are the perihelion. So one resonant angle involves the perihelion of the TNO, and the other resonant angle involves the perihelion of planet 9. So let's see how they evolve. In green here, it's this angle, and in black, it's this angle. So you see large oscillations, we call it the libration. This is not the libration in the mean-motion resonance. The libration in the mean-motion resonance is short periodic on this scale and gives the thickness of the curve. This long periodic oscillation is perfectly coupled with the libration of the longitude of perihelion, and it's actually the shift of the resonance center. Okay, it's not the libration. And as you can see, the black angle, which is this one, oscillates less, with less amplitude than the green one. So we think that this is a better angle to start with to build an analytic model. Okay, so this will be our resonant angle in the following. So how do we construct our analytic model? So it's a planar model for the moment. We go to space later. So we start from the canonical action angle variables, one related to the semi-major axis, conjugated with the mean longitude, the other one, which is the angular momentum deficit, related with the longitude, conjugated to the longitude of perihelion. So then we introduce a set of resonant variables. As I said before, our mean motion resonant angle will be phi. The phi is this angle with the perihelion of the planet, not the perihelion of the TNO. So it will be conjugated with the lambda, the semi-major axis. It's an angle that makes oscillate the semi-major axis and without an influence on the eccentricity. The other angle we want to keep will be the difference in the longitude of perihelion, which will be related to gamma. And then we have two angles, the mean longitude of planet 9 and the perihelion of planet 9 with their own conjugated value. So we do some average over the fast angle, only one, of course, because we keep the resonance relationship. As I said before, because we are working with extreme eccentricities, there is no hope to use series expansions. So we do this integral with a numerical quadrature. Once we do that, because of the D'Alembert rules, we know a priori that the final average Hamiltonian will depend only on two angles. One is the critical angle of the mean motion resonance, phi, and the other one will be the difference in perihelion longitude. These two angles move with completely different time scale. This is a mean motion resonance angle, so its frequency will be square root of the mass of the perturber, and this is a secular angle, so its frequency will be linear in the mass of the perturber. So this is a sort of fast, but the real fast degrees of freedom has disappeared. So this is the second, the sort of semi-fast degree of freedom, and this is the slow degree of freedom. So we can try to study the dynamics with an adiabatic approach. Okay. So basically what we can do is to freeze this degree of freedom and study this dynamics for various values of the slow degree of freedom. This is what we do here. So for instance, this is the mean motion resonant portrait, semi-major axis versus the critical angle of the resonance, for four different values of delta var p. So let's take first that delta var p equal 180 degrees, perfect anti-alignment between the orbit of the TNO and the orbit of the planet. So the mean motion resonance has a stable equilibrium point at for phi equal to 180 degrees. But if delta var p changes and go from 180 to 140 to 100 degrees, you see that the center of the resonance shifts from 180 degrees towards 90 degrees. And this gives exactly this kind of slow oscillation coupled with the libration of delta var p that we saw before. The other important thing to notice is that the libration region here is not bounded by a separatrix that starts from a homoclinic point. It's bounded by these two vertical lines. And these two vertical lines are collision lines, because we're working with a very eccentric planet and we are working with a very eccentric TNO. The orbits, as soon as you change the phase, they intersect each other and they can collide. And as you can see, as delta var p changes, these collision lines also shift, but they also narrow down. Okay. So there is some critical value of delta var p for which this area of stable libration squeezes down to 0. Okay. And so delta var p can never be bigger than that because there is no more libration at the center. So now we can take, as I said, an adiabatic approach. So we can consider a body librating very close to the resonance center, basically on the stable equilibrium point. And as the secular dynamic will slowly evolve, the dynamics in the resonant degree of freedom will change from one diagram to the other, but the body will always stay to the center because there is an adiabatic invariance there. Okay. So we can follow an orbit at the center of this A phi libration, and as delta var p and the eccentricity will change, my orbit will always follow the center of this resonance wherever this center will go. And so this allows to reduce the Hamiltonian to 1 degree of freedom just in the secular degree of freedom that I will show in a second. More formally, this can be seen as the equivalent of introducing action angle variables for this librational motion, then to averaging the Hamiltonian over the libration phase, and taking the limit of the action to 0. So this is the secular diagram that we obtained. So this shows the secular evolution of the eccentricity of the TNO as a function of the change of delta var p, the difference of its perihelion with the perihelion of planet Earth. So to guide you a little bit with what I said before, look at these points. Right? So these are points that shows some eccentricity and different values of delta var p. So for instance, when we are here, the mean motion resonance dynamics is exactly this one shown in this panel. When we are here, the mean motion resonance dynamics is that shown in this panel. And when we are here, the mean motion resonance dynamics is that shown in this panel, and that's where the collision curves shrink to 0 the libration amplitude. Okay. So that's why we call in this secular diagram, this is the collision locus. It makes sense to follow the dynamics only inside of this region. And then the level curves of the Hamiltonian gives the secular evolution, so which give a coupled oscillation of the eccentricity with the libration of delta var p around pi. And this orange curve that is plotted over the level curves, it's actually the result of the numerical simulation I showed before. So there is a perfect match between the analytic model and the analytic model and the numerical simulation. As I said before, so the resonances close to the planet 9 only have a stable region when the perihelia librate around 180 degrees. The distant resonances can have orbits with circulating perihelia. So what happens there? So this is, for instance, a numerical simulation for a body in a 3-to-1 resonance. And this shows that the difference in perihelia in this case circulates. So the eccentricity oscillation is very minimal. And because the perihelion circulates, only one of the 3 possible critical angles of the motion resonance, of course, is in libration. The other is to circulate. And in this case, it's the one that combines the perihelion of the planet with the perihelion of the astronaut, on the TNO. So if we can do the same kind of approach as before, and this is what we get. So this is the dynamics in the mean motion resonance. We have 2 libration points, one with phi res librating around 0, and one with phi res librating around 180 degrees. Like before, we don't have a formal separatrix, which is originated by an homoclinic point, but the 2 regions of librations are separated by the collision curve. The difference with respect to what we saw before in the 3-to-2 is that with the motion of the longitude of perihelion, this figure shifts a little bit left and right, but the 2 collision curves never merge together, squeezing the region down to 0. So you can follow a body close to the center of the mean motion resonance and compute the secular diagram, and this is what you get. And you see that the secular perihelion is in circulation in this case. And again, in these plots, the orange curve is what we see in the numerical simulation. So we have the libration of phi res around 0 and the circulation of var p inducing a very moderate oscillation of the eccentricity. So again, a very good match between the numerical result and the analytical model. So it's clear that the key for stability, for survivability for the age of the solar system is to be in motion resonances, unlike what Burst said. And so all the distant elongated TNOs not only should be maybe anti-aligned with some non-anti-aligned with planet 9, but they should be in resonance with planet 9. And on this, I would like to highlight this work published last year by Miloland and Laughlin. So they try to look if there is an orbit of planet 9 that can put everybody in resonance, because everybody should be in resonance. It's not trivial. You don't have one body, you have many, you have 7 or 8 bodies. No, you want to put everybody in resonance. The complication is that unlike for asteroids, well, you know what are the orbits of your asteroids, these TNOs, which have huge orbital periods, have huge error bars in their orbits. So you don't have an orbit, you have a PDF in their orbital element distribution. So what they did is a very sophisticated statistical study where they sampled the PDF of each of these long period TNOs, and they tried to find if there is a planet, where is the planet that maximizes the number of samples in the PDF of all the TNOs in resonance. Okay. And the result is therefore a sort of probability distribution of what the sum major axis of planet 9 should be, in order to maximize the probability that all the distant TNOs are all in resonance at the same time. And as you see, it's not noise, right? It's quite a structured plot with a clear peak at 670 AU. That's the position where most likely semi-major axis of P and 9 in order to put everybody in resonance. In that case, for instance, Sedna would be in the 3-to-2 resonance with P and 9, so the plots I showed before. 2000 CR105 would be in the 5-to-1, VP113 in 4-to-1, and so on and so forth. You can also compute what will be the phase of planet 9 in order to have everybody in resonance, because of course you have to have the critical angle of the resonance close to the center. And they find bad news. The planet should be near a field today. So that means that it's far away, and if you have a planet of about 10 Earth masses, with this kind of sum-major axis, with the eccentricities that are needed, 0.6, 0.7. So this planet is beyond 1,000 AU now. So it's magnitude 24, more or less. Give or take a couple of magnitudes. So very hard to find. Very hard to find. And the orientation of the orbit, because it's anti-aligned to the group, is such that this aphelion should be close to the Milky Way. Another complication. It's not really in the Milky Plane. It's in the Whale constellation. It's very close to the Milky Way. So very hard to say it, but the chase is on. So up to this point, I only discussed about the clustering of the longitude of perihelion, which is a real dynamical phenomenon through this mean motion resonance and the secular dynamics in the mean motion resonance. But I didn't mention about the clustering of the argument of perihelion. Okay, so now let's talk about that a little bit. So if the longitude of perihelion is clustered, having a cluster in argument of perihelion is equivalent to having a cluster in the node. Okay. And actually, so I will focus on the clustering in the node because it's much simpler to understand. So what happens? That if the orbit of planet 9 is inclined, and planet 9 is far away, so for the distant trans-Neptunian objects, the Laplace plane is not the invariant plane or the ecliptic of the 8 normal planets of the solar system. It comes very close or coincident to the orbit of planet 9. So if you take a distant and elongated TNO, it will have an orbit. This orbit will precess, not around the ecliptic, but will precess around the plane of planet 9. So by precessing, so first you have a plane like this, and this is the descending node with respect to the plane of planet 9. Half a precession after, this will be the orientation of the plane of the orbit, and this, the descending node with respect to planet 9 has been exchanged with the ascending node with respect to planet 9. This is the simple precession of one planet plane and out the other. But now look relative to the ecliptic. If this body is inclined relative to planet 9 less than the inclination of planet 9 and relative to the ecliptic, during this precession motion, okay, where I exchange the descending node with the ascending node relative to planet 9, I actually always have the ascending node relative to the ecliptic here. So by a pure geometrical effect, there is no resonance here, there is no particular secular effect, it's simply geometry. All the TNOs which have an inclination relative to planet 9, which is smaller than the inclination of planet 9 relative to the ecliptic, will have a node that appears to librate relative to the ecliptic, even if it's nothing to do with the resonance. And of course, if the node librates and the longitude of perihelion librates, also the argument of perihelion librates. Now you will say, okay, but now let's take some TNOs which have a large inclination relative to planet 9, larger than the inclination of planet 9 itself. And in this case, yes, as this orbit precesses around the plane of planet 9, exchanging the descending node with the ascending node, we will have the same exchange also relative to the ecliptic. So these bodies will appear to have a node circulating relative to the ecliptic, and therefore the argument of perihelion should appear to circulate as well. The point is that these bodies don't exist because they are so inclined relative to planet 9, they are unstable, and they are very vulnerable to an inclination instability. That is what we show here. So this is again now a number of integrations of TNOs which have initially a non-negligible inclination relative to planet 9. And some of them, those which can reach sort of 15, 20 degrees inclination relative to planet, those which have a very small inclination relative to planet 9 are stable forever. But if you take bodies that can reach 15, 20 degrees relative to planet 9, at some point they can develop a huge inclination instability, which brings the orbit to be even or retrograde. And we do actually observe bodies at very high inclination, around 90 degrees, and even retrograde objects today. Why there is this very high inclination excursion? Well, there is a resonance now, and that we have identified. The resonance has this critical angle. So it's 2 times the longitude of the node of the TNO relative to planet 9, to the ecliptic. Ecliptic has no meaning, dynamical meaning, minus the sum, not the difference, of the longitude of the perihelion. And this angle is conjugated to this action, and this is the portrait in action angle variables, and we see that the evolution of the action is perfectly correlated with the evolution of the angle, and the slow motion of this angle theta is the one that drives the action to very large values. If this harmonic were alone in the Hamiltonian, there would be a constant of motion, which would be this one. Now this is interesting because if you can see, so if the eccentricity is large, which is the case for all these elongated TNOs, this action is very small. Okay? So by trading off eccentricity with inclination, you can move the inclination from 0 to 180 degrees. So this is a real powerful resonance that can turn an object, an orbit, from planar to absolutely retrograde. In reality, this constant of motion is not perfectly constant because it's actually conjugated to delta bar p, which keeps vibrating. So it's a complex motion. Okay. But still, this allows excursions of the inclination from 0 to very large values, as those that I showed here. So in summary, what can we say about the dynamics induced by planet 9? So most of the bodies surviving to the present times on orbit that intersect the orbit of planet 9 have to be in motion resonance. And as we've seen in the paper by Miloland and Moorhead and Laughlin, this can be used to put quite strict constraints on the orbit of planet 9 today. The region of stability in the closest mean motion resonances, like the 2 to 1, the 3 to 2, the 4 to 3, and so on, is characterized by a libration of the difference in perihelion around pi. So you can only see anti-aligned orbits. Instead, if you go to more distant mean-motion resonances from planet 9, like 321, 421, 521, you can have both orbits in libration around pi or in circulation. In that case, you can see bodies with any kind of orientation. If the orbit of planet 9 is inclined, and it has to, because we do see the clustering in argument of perihelion, the orbit of the distant TNOs precesses relative to the plane of planet 9, and so if their inclination relative to PN9 is small, their node relative to the ecliptic appears to librate. So this is not a resonance, it's not a substitution, it's pure geometry. And of course, if the node librates and the perihelion librate, also the argument of perihelion librates. But again, this is not a double resonance, it's a geometrical effect, because the only resonance is for the difference in the perihelion. And then the orbits which have a larger inclination relative to planet 9, which in principle could circulate also relative in the node relative to the ecliptic, are unstable. They develop very large inclination. They can even become retrograde. So the secular dynamics become fully 2D and fully chaotic, and eventually these bodies become eccentric across the Neptune and Jupiter, and they are released. So planet 9 can really confine the TNOs in both the longitude of perihelion and argument of perihelion through resonant dynamics and through geometry. But this confinement is not absolute. As I said, I repeat, for instance, in some resonances, you don't need to be anti-aligned because the dynamics is such. So there is a preference for anti-alignment, but this is not an absolute preference. So the observers, when they find an object in another direction, should not say, this is the proof planet 9 doesn't exist. What one has to look to is at the distribution, the probability distribution of the orientation. So now the natural question, does this planet exist or not? And I will not answer this question, I will let you think. But I will list a number of advantages and disadvantages of this planet to explain features that we see in the solar system. And then you can decide if you are a believer or a skeptic. So there are three strange features, observed features, that planet 9 explains very well. So the confinement of the longitude of perihelion, which, as I said, is a sort of probabilistic effect, because you can have some bodies that circulate, and also you can have some unstable bodies that are still around. So for instance, if you take all the simulations together, this is the evolution of delta var p as a function of, after 4 billion years, this is the delta var p as a function of semi-major axis. And you see that the very majority of the bodies surviving the simulations have delta var p clustered around 180 degrees, but there are some that have any kind of delta var p. Okay? And the dots are the real objects observed so far. So there is a clear predominance for having delta var p equal to 180 degrees with a few outliers. But they are not by itself a proof, as long as they are a few outliers. They are not by itself a proof that the planet is not real. It explains also the nodal confinement. I don't have a figure on that. And it explains the origin of this high inclined, even retrograde population that we do observe, as I said. These bodies that I show here are real TNOs that have inclinations, as you can see, bigger than 60 degrees, some of which as big as 140 degrees. And if you plot their inclination relative to their argument of perihelion, and you compute with the tracks of all our simulations in this theta resonance, you see they match quite well. So I would say the planet explains this distribution as well. On the flip side, there is a new work by Nesvorny et al., also an author, but David did most of the job, where he's modeling the flux of short period comets in a very complete simulation that starts from the beginning of the solar system and acts the instability of the giant planets to build the Oort cloud and the scatter disk, and then follows these objects throughout the age of the solar system until they come back as Jupiter family or Halley-type comets today. And of course, this model has been done without planet 9, so just using the 8 planets that we know, and including the putative planet 9, in this case with mass a little bit higher, 15 Earth masses. And these panels show the expected distribution of the Halley-type comet in the model, in the solid, and what is actually observed as dashed lines. This planet gives the cumulative semi-major axis distribution. This planet gives the cumulative inclination distribution. This planet gives the cumulative perihelion distance. This panel gives the cumulative Tisserand parameter distribution. It's a perfect match. It's amazing. If we include planet 9, we still get a relatively good match, but worse. So the fit degrades a little bit. For the Jupiter family comets, it's almost the same. The Halley types seem to be quite sensible and normal. Right? Halley types go very far. So they really go into the region of planet 9. And then, as you can see, the comparison between the model and the data spoils a little bit. And to my knowledge, this is the only argument against planet 9 existing today. Okay. But the result is not that bad, and maybe this planet 9 was a little bit more too massive. I would favor more planets of the order of 5 to 10 or 8 to 10 Earth masses, for which probably the fitting would be better. But this is the situation, so I'll let you judge. If you be a believer, I'll let you decide if you want to be a believer of the stack. I can take your questions.
So we have time for questions.
Yes, thanks. In this last work, does it depend on the location of the planet 9? Because they have to choose something.
Yeah. Here, planet 9 is moving because this is a 4 billion year simulation. I'm not sure we don't have a specific phasing, so we've not done an exhaustive exploration.
No, I mean in the work of Nesvorny.
Yeah, exactly. So we have not done an exhaustive exploration of the possible orbits of planet 9, their mass, and their current longitude. So I hope that there is a way to solve this.
To find a constraint.
Yeah, an additional constraint, and maybe simply by going back to the orbit and lambda that is claimed by Miloland and Laughlin, maybe we can get something better. And we are working on this, so far that's possible.
Thanks. So if I get it right for the previous part of the talk, everything you should find there should be resonant, but there could be also non-resonant stuff which are still have a higher probability of being anti-aligned, but they are temporary. Is that correct?
There are anti-aligned, there are temporary stuff.
Temporary.
And the temporary stuff is hoping for more resonance to another, right? And there is again a tendency to anti-alignment because of the secular diagram, the first I showed before. But you can also have some circulation and yeah.
No, because you can see the blue lines actually there, so even in the first run, most of them should be resonant over there.
Yes.
And one more, just one last question. And for the last part, for the work with David, is Planet 9 there from the beginning of the simulation? So does it participate in stability?
Yes. But it doesn't participate too much because it's very, very elongated, and its perihelion is already
so it's
high up.
It's not considered to have come from the inner system.
No, it's considered to have been implanted in an area. So what we do is we enact the NIS model, and we consider that planet 9 was in place well before the NIS model during the giant planet acquisition, which what I think happened.
But could be also the other case.
If the planet 9 is ejected in the events of the NIS model, then it could be a more complicated dynamics. I don't like that because if when you eject planet 9 from the planet system, in order to trap it on an orbit with planet 9, you need to have a strong galactic tide, like a cluster. Okay, if the instability is over, you can still be in a cluster, no problem about that. But then you will not create a North cloud, because all the comets would be trapped on the 1,000 AU centimeter axis and not 20,000 AU centimeter axis. So if planet 9 has been ejected during the NIS model, we need to prove that the Oort cloud doesn't exist, and it's actually an illusion due to some way, the way the long period of comets are transferred, and so it's just a steady state structure and not a reservoir. But this is not enough.
Okay, we have time for one quick question.
Is it hopeless to really observe planet?
No, not at all. No. Planet 9, if it exists, it will be found. So to a magnitude 24 is that can be observed with big telescopes of the order 6 to 8 meters, which do exist. The problem is that the current telescopes, big telescopes, have a relatively narrow field of view. So people are looking more or less in the direction where the dynamics seems to suggest the planet is. But very soon we will have a new telescope, the LSST. The LSST will scan the full sky every week at magnitude 24.
Okay.
So that survey will clearly find the planet if it exists, or basically will rule it out. Of course, absolutely consider that.
Okay, thank you very much.